everybody to lecture 6. We had started a little bit into chapter 2, which is where we got introduced to the term ISA or ISA or instruction set architecture. And it's basically the vocabulary of the computer. And we took a look at some simple examples of C code, and I promised you'd be able to follow along what the assembler did, even if you'd never seen assembly language before in your life, as long as you've done, even some kind of programming. So what we also talked about was how you could compile individual lines of code. Stop sharing a little bit and make sure we get people. All right, there we go. Just remember, when you join the meeting, you're muted by default. I'm going to need to, guys, pause for just a second here. I'm still, listen, don't unmute yourself. I'm muting you. Don't touch. There we go. All right, you're muted. Okay, I'm going to pause the recording for a second because there's an air conditioning guy here to fix my. Okay, thanks. Thanks for letting me do that. All right, so go back to sharing my screen, and we'll pick up where we were. So you'll remember that with some languages, they take one line at a time and immediately convert it into assembler, just like we saw with that C example. You type it in, you hit, but other languages like C, usually you write the whole thing first, and then it's passed through another program, a compiler, be improved as much as possible before being given. So kind of the rule of thumb is if you plan on running something thousands of times, hundreds of times maybe, then compiling it makes sense. It's worth it paying that upfront delay of having to go through makefile and all that. If it's something you're going to run once, like a command to DOS, like show me a list of the files in my directory, ls return, dir return, then why would you want to go through and compile that program? Just interpret that command right now. All it's going to do is go and pull a compiled program that actually does the work anyway, so you might as well. So we mentioned there are places where instructions and computers can put intermediate values. So if I wanted, back to my C example here, if I want to add G and H together, where are they? Where will I find G and H? Well, with systems like MIPS, everything has to be loaded into a special bank of very high speed, tiny memory called registers. And let me pull this up. Okay, whoever joined, you're muted automatically when you join. So if you click the mute button, you just unmuted yourself is all. All right, there we go. So G and H in this case are not yet in registers because those are not the names of registers. In real MIPS code, what you find is a list from a different table. So we're going to spend some time and go through what that table of registers looks like. Registers are special memory because they're built on the CPU out of the same silicon, therefore they run at the same clock speed. So if you think about it, it's a cart and horse kind of, or chicken and egg kind of problem. You can't have a CPU ever run at clock speed if it has to go and fetch instructions, it has to decode the instructions, it has to go and grab the operands for the instruction out of memory, and that memory where the instructions are stored and where the operands are stored can't keep up. So if that happens, then you can set whatever clock speed you want on your CPU, but you'll never achieve it. You'll never see it. So there's a very small amount of precious memory that does run at clock speed. In fact, if you can't make memory that runs at that speed, you can't have a CPU that runs at that speed. So they make it out of the same material on the same chip. So it's small in number, not just because real estate is scarce. It turns out mathematically, we really don't need that many registers to run a program because the context is not that great, meaning it's unusual for one line of code to use a variable that's not going to get used until 20 lines later. It's usually going to get used in the very next line of code. So you'll put something in a register, you'll run a command that uses that entry in that register, and then you move on with your life. So what's not shown in this example, back to C again, is the loading of the values of the variables G, H, I, and J into memory, into registers. So you may prompt the user to give you numbers, you may pull them from the hard drive, you may get them over the internet. They may be the results of other intermediate computations, but however you get them, you're going to have to put them in this special memory called a register before you can call these commands. That's not the case for every type of command, and it's certainly not the case for every type of architecture out there, but it's largely the case for MIPS. So MIPS has 32 registers, and that's a common number across all architectures. And each one of those registers is 32 bits wide. So here's kind of the first key thing you need to let sink in. The size of the register file, however many bits it is the size of the architecture, we say, of your computer. So if you're running on an 8-bit computer, your registers are 8 bits in size. If you're running on a 16-bit computer, you'll find that your register is full of 16-bit registers. Let that sink in, right? So there's a direct relationship there. And furthermore, with some exceptions with people that get fancy with their architectures, generally speaking, an instruction fits in a single register. So in MIPS, it's actually ironclad. Every single instruction in MIPS can be completely stored 32-bit register. So if you're trying to tell the CPU, here's what I want you to do, here are the operands you need to do it with, and oh, by the way, here's where I want you to put the result, you're going to have to say all of those things in 32 bits. So we talked last time about this row of pins on the side of the chip where you line up all the 1s and 0 values that are going to convey to the computer exactly what you want it to do. And then when the clock cycles, when it strikes 1 or whatever, you're going to release the hounds and let all those high and low voltages that represent 1s and 0s into the computer. And somehow the CPU is going to know what to do. Well, we're going to see how it knows what to do. And to kind of give you a sneak peek, every 32-bit instruction is a little data structure. It's got a part of the 32 bits that's reserved for the name of the instruction, the name of the add, subtract, multiply, shift, load, store, test a logical condition, etc. Branch, jump, reboot, put something on the stack. All those commands are part of this little data structure that's only 32 bits long. Depending on what that is, will dictate how the rest of the bits are laid out. It's a mathematical instruction, then you're going to need, we know from last time, 3 things that you're going to have to tell MIPS. You're going to have to tell it the location of the 2 source operands, and you're going to have to tell it the location of the destination operand. So if we go back to slide 4, remember it's an arithmetic instruction, and we learned in section 2.2 that every arithmetic instruction in the MIPS architecture has 2 sources and 1 destination, and it meant put into A the result of adding B and C. So I'm going to have to convey in 32 bits the fact that I want to add C and put the result in A, and I'll show you how that stuff happens. So this makes learning assembly a dream when you have an instruction set architecture that's very regimented and regular, and it'll help the light bulb go on a lot faster. We will take a look at the way ARM and Intel do things frequently, just so you have an idea of kind of how much further you need to go to really be productive at working with those systems. So we give them numbers, but we call them by names, but the computer gives these 32 registers numbers. So if you have 32 registers, how many bits do you need to keep track of 32 different things? Well, one of the things that you need to get good at doing in this class is counting by 2, meaning powers of 2. So that's one thing that's going to be helpful to you. But another thing you're going to need to know some basics of are how logarithms work. So let me close a couple of these windows off, and basically what I'm asking is 2 to the what will give you 32 combinations. And the way to do it with your fancy scientific calculator is to take log base 2 of that number, and that will give you 5. So here's my 32-bit instruction. And somewhere in here, I have no idea where, I'm going to tell the computer that my first operand, I called in my C code the letter A, but it's stored now in a register. And I'm going to tell the computer which of the 32 registers it's stored in, giving it a 5-bit integer. Because if it's 5 bits, I can tell it which register it's in from the number 0 to the number 31, which is 32 different numbers. So let's say I tell it it's in register 10000, then I know in my bank of registers, I go to that one, which is the 17th register. It's the number 16 in decimal, but I started at number 0, for example. So I only need 5 bits out of the 32 to tell MIP where to find the first operand, because it's got to register. I only have 2 of them, and I only need 5 bits to tell you an integer between 0 and 31. Furthermore, you can see where this is going. My next operand from that example was B, and I'm going to give it a different 5-bit number. And again, that's going to tell it where B is. So the computer will know to go and pull that value right off the chip from this data bank of registers. So these are the registers. And this is just an example of one instruction word, we'll call it. The source, the other one will be over here. I think what we did, if I remember right, I'm saying this a little wrong, we added B and C, didn't we? And then we put the result in A. So do not take to heart right now the location of these things on the diagram. Don't infer a bunch of things. Don't infer the order. I'm not telling you for sure that A comes first and then the next 5 bits are B and C. Don't worry about any of that yet. Just wrap your head around the concept that I have just discovered that I can tell the computer in only 5 bits where each of the operands, the 2 source and destination operands will be located. So my third one, maybe C, is down here, 0, 0, 0, 1, 0. All right, so that's where those things are going to be. That's where those things are going to be stored. All right, so I've used up, what have I used up? I've used up 15 bits, and I had 30 to begin with. So I've got 17 bits left. So we're going to take a look at how those 17 bits get managed. All right. So we've talked about the 32 registers. We've talked about ways. We've taken a peek at how we might start using some of them. We've got 17 bits left, we discovered. So we're going to have to, at this point, just basically communicate maybe one more thing, which is which instruction do I want you to run on those 3 operands. So assembler language gives, as I mentioned, names to these. So when you write a line of MIPS code, you're not going to be using the 5-bit number. You're not going to be using any number at all. You're going to use the name of the register. So I'm going to go to our lecture folder, and the first thing I'm going to pull up is MIPS reference data sheet, which is otherwise known as the green card in the industry. So I may also create a link here called the green card and just have it point to that file for you. And it's a 2-page PDF, and this is what it looks like. And what you'll see is it's got a list of all of the instructions that you will find in the base set. Then on the right-hand side, it's got some floating point and fancier instructions. But we're going to start by understanding what's in this side. So there's a bunch of rows in this. Each row is going to tell us a bunch of stuff. So let's start with the very first row, which is the command that we're interested in anyway, which is the addition command. So you and I would call it the add command. And fortunately, it's a very short word in the English language. And so we're able to fit it into just 3 letters. So if you start a MIPS command with the letters ADD space, it's going to get interpreted correctly. Okay, so once I know the command that you're trying to run and kind of the computer program name for it, which format does it follow? Well, what does that mean? Well, a format is the way you should interpret how to divide up the 32 bits. And as you can see in this column, for all of these commands, they only fall into one of three categories. In fact, mostly they fall into R and I with a couple of J's, and that's it. Where can we find out more? Well, we scroll down a little bit and we see this section called Basic Instruction Formats, and there's three of them, R, I, and J. Now we'll see this in the slides as well, but I want to start reinforcing what's on this card because it's going to be helpful to you in something like the exam, for example. So what this basically says is I have this rectangle, kind of looks like the one I drew. They number it from the right to the left from 0 to 31. So that tells me it's 32 bits in size rather, and bits 26 through 31 are set aside for something called an opcode, whatever that is. And then 21 through 25, 21, 22, 23, 24, 25, that's 5 bits. That's RS, and then there's one called RT and RD, and then a couple of these other things. Okay, so like that's totally gonna lose you because it's doesn't have anything to do with A, B, C, or add, does it? Well, it turns out it does, because what is your first hint as to what it is you're asking the computer to do. And RS, RT, and RD stand for register names. Register, put 3 numbers in here. So let's go back up to the top where they're kind of showing us how to interpret these core instruction sets. I know add is an R-type instruction. We already established that from a second ago. And what I see is whatever the value is in the register, number RS, should be added to whatever number is found in the register, number RT. So RS and RT are register numbers. So if I go to that register number, I said you're going to find contents in it. So you're not trying to add the register number, you're trying to add what's in that numbered register. So I'm going to add them together and I'm going to put the result in a register number D. So these can be any 32-bit integers, and the destination is also 32-bit integers, so I'm going to have to start worrying about things like overflow. If I add 2 numbers that are too big, then I can't represent it in 32 bits. So both source operands are 32 bits and the destination operand is 32 bits. So that's going to limit me right there into how big a number I can represent. And I also have to figure out, how am I going to tell you that it's a negative number? How are we going to know that? If I look at other commands like subtract, which they've got down here, it's the same idea. You're going to subtract from whatever is in register RS, whatever is in RT, and you're going to put the result in RD. All right, so the last thing we see over here is something called opcode and function code. So these are 2 numbers. The opcode is in hex, and so is the function code. So what does this basically mean? For the add command, I see that if there's opcode and then a diagonal in the function code, I see 0 and a diagonal and 20. So that's telling me that for the add command, the opcode is 0, function is 20. So opcode we've seen. Opcode was this down here in the R-type instruction. So now I know what to put in bits 26 through 31. It's a 6-bit number, and it represents 0. So it's going to be 6 zeros. That's how you represent the number 0, right? So I'm going to put that in there. And for reasons I don't quite understand yet, I'm going to put the value decimal 32, which is hexadecimal 20, and they told us it was 20 in hex up above. I'm going to put that value in here, and it's 6 bits also, so that's plenty enough bits to represent the decimal number 32. All right, but I don't know why I'm doing that yet. All right, so let's go back to the slides and continue on and start now reinforcing a little bit of this stuff. We have the register names that we've looked at, and there's some rules around how you're supposed to use these. Now, most MIPS compilers will not enforce that you use the registers in the way you're supposed to, but you absolutely must if you expect your code to run on a computer with anyone else's code, because there's only one set of registers. It makes sense, there's only one CPU that we're talking about. And if you start switching programs around, the things that you've put in the registers have to be stored. We may have to take a snapshot of them and remember them, set them aside to let somebody else use the computer for a moment. And when it's your turn again, we're going to have to put what you had in the registers back. So that got old really quick. And so instead of making you store all of the registers, people started noticing things like, well, you know, registers are a really handy way of the user communicating values to a program. Like I was able to put A and B in registers, and it's an easy way for the program, convenient way for the program to communicate back to the user. Like I, put the result in a variable and looked in the register for that. But what about from one program to another? What if Excel needs to send a number to the HP printer module? Two different programs running on the computer, and Excel is just dying to send the number 6 for whatever reason, whatever that might mean, to the HP program. Well, what's a way for them to do it? Well, they could write it to a file, but that's very slow. They could put it in an area of RAM. Okay, well, that's slow, but not as slow as the drive. But if it really is something that tiny, like one number, well, why not in a register? I mean, after all, registers are the fastest type of memory you're ever going to have on your system. So maybe I shouldn't dedicate all 32 registers that for each program. In other words, when it's time for Excel to move out of the way and to let HP come in and have its turn at the CPU, maybe instead of taking a snapshot of all 32 registers and then clearing them out and then storing them over here with Excel so that when Excel comes back later, I take all 32 contents of the registers and put them in again. Maybe I only do that for some of the registers and I leave some of them alone so that Excel moves away, whatever values it had in those registers, and then when HP takes over and comes in and he looks around, he goes, oh, well, there's some numbers here in the registers. That's interesting. Wonder what that's for. And he runs his first line of code, and the first line of code says, grab whatever is in register T3. So as long as Excel and HP have agreed in where they're going to put these things that they want to pass back and forth, registers are very fast, efficient ways of passing small amounts of information between processes as well, including between the operating system and your program. After all, the operating system is just another program, and it's having to share the CPU and the registers as well. But only one program is running at a time. One program is running in the CPU. One program has control over all the registers. What we're talking about here is what happens when you move out of the way to let someone else take over? Do we need to clear all the registers out? So we made the split middle. So I'm going to go back to the folder again, and this time, lecture 6, I pulled the green card up from our extras folder, but where I should have pulled it up was from our lecture folder, because that's where I always try to put the things that we want. So if I come in here and look at this file called MIPS calling convention, that's a funny way of basically laying out and summarizing the 32 registers. And basically has a call to action that says, you really must follow these rules. So there's one register that's called $0. It's a special register name, and it's not one that you and I are going to use for anything other than hitting the value 0. We'll come back to that later. Then there's some registers here that have the value that we give a name V0 and V1. Okay, that sounds like 2 registers to me. There's one here called AT, and if I were to use $AT in my MIPS assembly code, if I were to use that as type that in as part of my program, when it got to the interpreter, it would be interpreted meaning he's talking about register number 1. Most of the ones that we're going to use are the T's and the S's and the A's. So basically in this sort of middle area around here. We're going to use a couple of the others as we get a little further in the class, but what you're basically seeing here is the decision that the MIPS architects made about how are we going to divide up this beachfront primo property, this real estate. And what we're going to use are a couple of registers to store return values from subroutines. So when HP is finished printing your Excel file and it wants to give you back a status code saying, yes, it printed, or no, I had an error, you can communicate that in a program with a number. If it comes back and the number's 200, it means they found the web page. If it's 404, it means the web page wasn't found. So V0 and V1 will be preserved when you come from a calling subroutine back to your main program. So we're just asking programmers around the world to please use register 2 and 3 for that purpose. We see temporary ones in here, T0 through 9, and those are not contiguous. They're 8 through 15 and then 24 and 25. Those are temporary registers. You can use them for whatever you want in your code, and it's fair game. As soon as you're moved out of the way, which will probably be in 1,000th of a second, and somebody else comes in, they can wipe you out. They're going to leave them there. The operating system will not clear it out, but whoever comes in, they can do whatever they want with that space. That's like public right of way. That's on the sidewalk. That's not, it's not really by you. Some of them, S0 through S7, these are ones that the operating system CPU will be very careful to observe, take a snapshot of, and remember. They'll set them aside along with you, and we're going to remember things like, where were you in your program? What line of code were you running? What were the values of the registers? What was going on? We'll take a snapshot of that, and then when it's your time to come back in and run, get some more CPU cycles, we're going to load those things back in there in the S registers. But no bets on some of the others. All right, so that's the idea behind that. There's also a website that will take you to GitHub, and I forgot to double click and load that up ahead of time, so we'll just pull this up here quickly, I hope, and see how quickly this page loads. These things change all the time, so I check them before. So this is a much neater looking table. You might find this more interesting. Also, how can you not be interested in reading what Internet Sad Boy has to say on GitHub? So here they're basically laying these out. You get to bring a cheat sheet to the exam. So this is the kind of thing that you might want to take a snapshot of or copy and paste, but the URL for this is in the lecture folder. Right? This one right here. Back to the slides. Gosh, we're barely making it through any, but these are short sections and they require a lot of discussion. If you are lost at this point, if you are falling behind, make sure you go back and listen to this again, because you will struggle until you get the basics of this down. All right, so why 32 registers? Because smaller is faster. You could have 1,000 registers, but for reasons I mentioned earlier, primarily the fact that we don't usually put something in a register and then use it for the first time 100 lines later. We usually put it some right before, like, you put the food in front of somebody when they're hungry, like they're going to eat it right then. So it's that kind of idea. So here's an example now of that C code using real. It's the same line of C code, and let's say we put F, H, I, and J in registers S0, 1, 2, 3, and 4. Why did we choose S0, 1, 2, 3, 4? Well, let's go look at what the S's mean. S's are saved registers. So what did that mean? That meant that whatever values you put in there will stay there, right? And they're not really going to stay there. They're going to get pulled out all the time. Probably even in the middle of running this program, it could be pulled out, but they'll be put back, turn again. That's what putting something in a saved register means, is the system will make sure to take a snapshot of it if for some reason you're yanked off the stage, and when you go back, you'll still have those. So my variables G, H, I, J, they are put in S1 and 2 and 3 and 4. And add those two things together and put the value in T0, put this intermediate value in T1, and then subtract the two from each other and put the answer in 0. Now, there are things that can happen that can mess you up. You could get pulled out in between this line of code and this line of code, and then when you come back, what's in 0 is obliterated. That can happen, but we're not going to worry about that now, because that involves talking about locking and atomic blocks of code, et cetera, and we'll have a chance to talk briefly about it, but just don't go there right now. Just assume that these 3 lines of code you'll be able to run without interruption. So that's the way we write variables that represent registers. Always a $sign, always a letter, and then always a numeral. And there's a couple of exceptions. If I go back over and show you, one of the exceptions was register 0, and we actually put $sign and then 4-letter 0, and then there's a few others down here that represent some things that we haven't really talked about yet, but we will. So far so good. So we've seen an example. These memory operands, you can also tell MIPS where to find an operand that's a little further down the road. That's not in a register yet. It's out in memory. So if you have something that's too big to fit in a register, like an entire array of 1,000 numbers, well, you don't have room for 1,000 things in registers. You've got room for 32. And some of them look like they're being used for other special purposes, so I probably don't even have access to all of those. So what do you do in that case? There's another way to use registers. And the second way to use registers is to not put the contents here, but instead to put the contents out in RAM. And RAM is much more voluminous. And let's say the number that you need is here because, there it is. Because the array that you're drawing starts here, goes through here in RAM, and then stops here. And right now, we're interested in the element that I've put here with the lines around it. So how am I going to tell the CPU where that is? There's a type of command that you can run that give a register number to, but the CPU will understand that what they will find in that register is 32 bits, like always, but to interpret the 32 bits not as the operand, but as the memory location where you can find the operand. So I can change the value in here as my program goes along, incrementing it word by word by word. It's an increasingly larger integer, and if I'm right command, it will know when it sees the value here in register 17 that it's talking about successive locations in RAM. So instead of A there, A is going to be over here. And whatever this address here is, let's say it's 01101, 0101101, it's half of an address. This whole thing will be what you find in this location. So I have one step of indirection to try to do. So my code might look something like, I want you to add what is in A20 to B64. I want you to put the result into C17. So how am I going to do that as an assembly language interpreter? Well, what I need to know, if you're talking about A20, is first of all, where does A start in RAM? A is going to start right here. And then you want me to take that address for A, and I will have that address for A stored in a register somewhere, and you want me to add 20 to it so that I step through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 20. Here it is. So that's where A20 is, and I'm going to grab the value out of here, and I'm going to store it in a temporary place in a register. I'm going to do the same thing for B, add the two things up. Now I have the answer. Where am I going to put it? I'm going to be given the starting address for C. Step, this said 17 here. I'm going to go 17 steps past that, and I'm going to stick the answer there. So that's an example of how RAM can be used to store that we need for a line of code in assembly. Right? So big data structures, dynamic data, stuff that changes, things coming in over the internet might put into RAM, for example. Things you're reading off the hard drive may very well be put in RAM. Things like that. You need a way to get back out to RAM, and it also gives you an idea of how things get back and forth. So to apply math operations, we're going to load values from memory into registers. So That's where A, B, and C, and D came from. And then when we're done, we don't tell you we're finished with your program by telling you the register number you can go find it in. No, you expect us to do more than that. Usually at the end of a program, you want us to print it on the screen or write it to a file. So that requires taking it out of a register and sticking it into someplace in RAM, either an address that the video display subsystem is busy looking over so it knows what to put up, or putting it into an area that the hard drive controller is busy looking over so it knows to write it out to a drive. All right, in RAM, all RAM around the world is addressed. So about what that means. So far we've looked at how to organize 32 bits into an instruction, the same size. 32 bits is the size of a register, and it's basically the building block. So when we go to RAM and we're going to put something in a register, you can probably surmise that we're going to grab 32 bits of RAM to fill the register. And if we put something from a register back out to memory, we're going to need to find 32 bits of space in RAM so we can put that in. So everybody knows that a byte is 8 bits. So we're going to have 4 of them to get to 32. Now, whether you're on an 8-bit system or a 16-bit system or 32, or if you're on 64, newer computer, if you have a 128-bit system, I'm impressed, good. But whatever the size of architecture is, what we know now is this represents register size and the instruction word size, generally speaking, some exceptions to that, lots of them with Intel. And however big this is, you can figure out how many bytes in RAM this equates to. So on an 8-bit system, you're going to be dealing with 1 byte at a time. Well, that's convenient because a byte is 8 bits, so they match. So have a byte out of RAM, it's the same size as the register, it's the same size as an instruction. So far, so far so good. Then the next thing we can do is look at 16 bits. That requires 2 bytes in RAM. Then if you are on a 32-bit architecture, every time you go to RAM to get something to put into a register, vice versa, you're going to be dealing with 4 bytes at a time. And then to finish this out, 8 and 16. So however big size this is known as one word, always. So if you're on a 32-bit system, like we are this semester with MIPS, in our book, our MIPS system is a 32-bit system. We have a 32 word. So this creates a problem because RAM over here doesn't give a hoot about what our word size is. It doesn't really care what architecture size we have, how many bits it represents, etc. It doesn't make any difference to it. It's only going to be built around the world in byte increments. Why? Why is that? So that regardless of the architecture you're using, if you pick RAM, it's going to be the same RAM that anybody else around the world is going to put in their systems as well, as long as the speed will function the way that the computer architect needs. They're not going to build a special type of RAM for 8-bit, 16-bit, 32, etc. And it drops the cost of RAM. You don't have to build as many different kinds. Therefore, each kind can be built in greater quantity, and it keeps the cost low. So it's going to require a little extra work for us. We're going to have a magic widget in the middle. Every time we pass a request to RAM to take something from us, we are going to give it a word address. So word addresses go in here. And on MIPS, the system that we're using, we know it's a 32-bit number. So that's going to be the address of a word. And what's going to happen coming out, it's going to have to be turned into 4 independent requests to RAM, because RAM doesn't know about words. RAM knows about one thing only, bytes. So if I want it to put something in a word number, I'm going to have a way of figuring out where in RAM that is. Take the first 8 bits of my word and drop them in here, and the next 8 bits are going to go in the next byte, and the third and the fourth parts of my word are going to go in here. Now, RAM thinks of these as 4 independent bytes. They don't have anything to do except that they happen next to each other, but we're going to be careful when we go to RAM and always convert word addresses into byte addresses. So that's the way to work. So think about it as a meal number at McDonald's. You're going to go in and order by a meal number, but background, they know that there's 3 things they've got to do. They've got to give the sandwich that you want, the size drink that you ask for, and then whatever the side is, a salad or French fries or whatever it might be. Right? So always that translation is going on. So if you tell them you want number 3, it means something different. They have extra work to do. All right, so not a perfect analogy, but I just want to give you that idea. All right, so memory is byte addressed, but we deal with words. Now in MIPS, in this book for our system, we use 4 bytes per word because our words are 32 bits. We need 4 bytes to get 32 bits together. So let's look at one other thing we do to try to keep from going crazy as we design one of these systems. Let's say this is a bank of RAM, all right? I've got 1,000 bytes in here. Somebody asks for a location, some room and memory to store the results of an array calculation. So they ask for, hey, give me some memory, allocate some memory. This would be like a malloc command in C, for example. Can I have some memory to put something in? You could artificially drop them in anywhere you want RAM, as long as it's contiguous. But something a little more careful than that. What we're going to do is divide up memory evenly, 4 bytes at a time. So inside of each one of these lines I've got, I'm going to have 4 bytes. Not drawing these perfectly. The visual is what's important. I think if I hold the shift key down, they're all perfect. All right, so when you ask me for a word, I'm going to take the word address you gave me, which is up here, and I'm going to multiply it by the number 4. And if you hand me word address 0, it points here. If you hand me word address 1, you're asking for the next word, right? 0 was the first word, 1 would be the one after that. Well, where would word 1 be? It would be a mistake to look at address number 1 in RAM, because RAM deals with bytes, and it's going to think 1 is the next byte after 0, not the next word after 0. It doesn't care about words. So we need to multiply it by 4 to make sure that when somebody asks for word 1, what they're really getting is byte 4. And when they ask for word 2, they're getting byte 8, 3, and byte 12. And now when you have this system here that multiplies your actions out by 4, asking for word 0, 0 times 4 gives you byte. It's going to give you this one, this one, this one, and this one. Remember, 4 bytes. It does that automatically. If you ask for word number 4, in other words, if I look in the address that you stored in a register and I use a MIPS command to say, please go get me the contents of RAM at this address, it's going to be treated as an integer, as a word number. It'll be multiplied by 4. It will get you to 16 in memory, and then it's going to add 1 and grab that and that and that, and it's going to grab these 32 bits that come back, store them wherever, in whatever register you told it to store them in. Right? So making sure that a word, which is basically what we're storing in here, making sure that a word fits within one of these boundaries perfectly And it never does something like this. Bytes are on one side of a multiple of 4, and the other 2 bytes are on the other side of a multiple of 4. That will never work. Doing it this way is called keeping things word aligned. They're aligned memory. All right, MIPS. The last thing we need to talk about is how do you decide how to store things in memory? And switch back to my pen again here. If I give you a 32-bit word, somebody's unmuted. So please take a look. If you just joined, for example, I can hear you typing. Olu Wesson, I think I'm mispronouncing your name. You may want to make sure you're muted. Okay, so let's say this is my 32-bit contents of my register. Say this is register T0. So it's got bits 0 to 32, 0 to 31, really. And I've divided it up into 8 bits in my mind. MIPS thinks of it as a single 32-bit number. And the only thing remaining is which one goes here. Is it this guy or is it this guy? Which one do you put in first? And that's going to spell out how the rest of the things go. Right, so which is the big end of this thing and which is the little end? Well, these are the least significant bits. So this is the little end, and this is the big end, where the more significant bits are. It's also where the higher bit numbers are. So if you put as your first byte word the value that's down here at the little end, you are said to have a, sorry for this, it's not politically correct, we need to change it. It's called a little endian format. The value that you put in this byte first is the one that came from the more significant bits, then said to be a big endian architecture. This is invisible to programmers. It's invisible to almost everyone. Once writing and dealing with registers and stuff, this has nothing to do with anything. This is only something that this black box here has to worry about. He's the only one that ever has to deal with this thing. So if you're a big endian system, you're grabbing these 4 contents, it needs to know to fill in the register by putting this one here, this one here, this one, and this one here. If it's a little endian system, on the other hand, and it gets things out of memory, it's going to put this one here, and then this one here, and so forth, right? Exactly backwards. But whatever it is, it's going to fill your register and hand it to you, and you're just going to be oblivious to what's going on in RAM. You don't need to worry about it. But it's an important concept, and believe it or not, people do manufacture, still to this day, both types of systems. MIPS is a big endian. So the most significant byte, the left-hand one, is at the first byte in RAM. All right. So here's an example to kind of back that up. Here's a memory address that shows how it gets broken up into individual, bytes, for example. So if I want to show you the from the point of the CPU, they think that this is word 1, word 0, word 3, word 2. These are word numbers here in the middle. CPU thinks. And so therefore, if you're writing code for the CPU, you're going to write code referring to things by these numbers. If you, for some reason, have to tell the CPU, I want you to go to memory and get me word 3, you're going to tell it 3. You're going to tell it that. And what will happen in RAM is it will be multiplied by 4. It will be converted into byte addresses. So when you asked for word 3, it got converted to byte 12, 13, 14, and 15. All right, so here's an example of that. So back to our C code. This time I want to add H to the 8th element, A. Okay, and I want you to put the result in G. So H can go into a register directly because nothing fancy about it. It's just a value. I grab it out of memory, I load it into register S2. And the command to do that, by the way, would to load word into whatever address you got, whatever mem location we'll look at in S2. So it looks kind of similar. It's got an opcode and a couple of operands in here, but we'll show that here. So magically H is already in some register. We'll put it in S2, and we need to tell you how to get to the 8th element of array A. Well, what size is an element of an array? Well, by default in C, an element of an array, when you allocate or define a variable, it's the size of whatever a word is in that architecture. So if you allocate memory for an array with, say, 20 elements in C on a MIPS computer, each one of them is going to be a word in size. So each one of them will be 4 bytes. And what did I say, 20 elements? You're going to allocate 80 bytes in RAM and set them aside for this. And you'll refer to them 0 through 19 because that's 20 things, but it'll actually take up 80 bytes to get it done. So in order for me to interpret what the C programmer was really trying to tell me here, I need to remember that to him or to her, 8 represents the 8th word, not the 8th byte. So I'm going to need some help. You're going to have to tell me where you began array A in memory. You're going to have to give me a specific memory byte address for that. And I'm going to store that someplace. So I'm going to have to load that into you and count it off. So here's my load word command. I want you to load into a temporary variable, T0, whatever the word is that starts 32 bytes after S3. Well, what's S3? Well, S3 is the register that contains the starting point of A. So S3, let me show it here. There we go. S3 points to, we know this because what we just talked about, it's going to point to some word. So let's say S3 points right here to this byte right here. So whatever the byte address of this is, it may be 16384. That's what it is. I stored that value, 16384, divided by 4 maybe. It depends on the system, but I'm going to put that in my case into S3. Now in MIPS, it's actually going to put the starting point in there. And then add 32 to it. So when you write code in MIPS, here's an example of where you have to do the work for the system. You're going to have to take the element number, multiply it by 4, and how many bytes past that. So S3 is said to be a base register. It's being used as a base point in this case, because in that register, I'm storing the starting point of my array. It has the base address, and I'm going to add 32 to it. What's that going to do? It's going to step me up 1, 2, 3, 4, 5, 6, 7, 8, 29, 30, 31, 2. Here is going to be my A8 here. So I need to do a load word starting at this byte address. This byte address is whatever the base was plus 32. And that'll get me here. And that's exactly what I calculated with this number. This means 32 plus whatever number is in S3. And we'll interpret this as an address in RAM. It can't be floating point number. It can't be text, negative. In this case, because load word knows what you're trying to tell it is an address, when it looks in S3, it's going to know to interpret the 32 bits it finds in S3 as a positive, unsigned integer. And it will add 32 to it. And if 32 puts you past the last valid address in your system, you will have a memory fault and a dump. Your program will crash. Whatever that is, grab the contents of that RAM. You're going to drop it, pull those 32 bits out of RAM, bring them back over, and store them in a row in register T0. And in register T0, since now you're back at the CPU, the least significant bit here in bit 0, and the most significant bit will be here in bit 31. So if this is a 0 or a 1, it's going to be 0 or a 1 times 2 to the 31. That's what it means to be in the 31st position. Down here, this is a 0 or a 1 times 2 to the 0. It doesn't have as much weight. So it'll be stored exactly the way you think. If I give you your bank balance of $1,234, you're going to know that this is times 10 to the third times 10, because it's in the 0th position, first, second, and third position. You know it doesn't mean $4,321. I wish it means that. So same way like you've always learned, don't get confused. When it stores it into RAM, it will store it in the opposite byte order, but you'll never have to deal with that as a programmer writing code like this. So now that I've got it into T0, what was it I wanted to do 10 minutes ago? I wanted to add it to the integer that's in H. And because I'm using the add command, I will look in where I put H, which was in S2, and I will treat whatever value I find in S2 as an integer. But now my question, how are you going to know whether it's a positive or a negative integer? In fact, how are you going to know whether the number that you got out of A8 is a positive or negative integer? All I have are the 32 bits. There's not like a sign bit to the side of it as well. It's not really 33 bits, just 32. So if I want to denote that some numbers are positive, then some numbers are negative, I'm going to have to use some of the possible bit patterns that I have with 32 bits and set them aside to mean something different. Right, so we'll spend a whole lecture on that topic right there. So if I want to store the result instead in A12, then I'm going to take the base address of A, which was in S3, and I'm going to add 48 to it. And here was where I loaded A8. This was the address of A plus 32 gets me up to A8. I'm going to use a load word. It's going to cause 4 bytes to be loaded from that location. And I'm going to pull them back and stick them in T0. I added H to it. So now I have H plus A8 done. And I put that result, wrote on top of my variable, overwrote it, putting it in T0 again. And now I'm going to store it out back to the array in RAM. So I'm going to take what's in T0, and you'll notice this time the source is T0. And the other two commands, the destination was T0. Well, how do you know whether it's supposed to be the source or the destination? Well, I go back over to my, and I look at store word, and what store word tells me is I'm going to put to memory at the location of whatever the register RS, number RS has in it, plus any sign extended immediate, which we'll talk about later, and store there what is currently found in register RT. So it will give us the nomenclature and tell us exactly how to interpret. That's how you'll know this is the source versus the destination. We'll see some more examples to help you. But where I'm going to put T0 is 32 bits. I'm going to start with first byte at 48 bytes past S3. All right. Hopefully I beat that to death, and you guys follow that stuff along nicely. I didn't want to change the order of my stuff. So what's the difference between registers and memory? To kind of recap, registers are faster. They're on the CPU. They run at the same speed as the CPU. Just remember, if you can't get the operands you need in time the next clock cycle, then you can't run the instruction next clock cycle because you don't have the operands. If you can't run the instructions at the clock cycle you want, then you can't have that clock cycle. You're not really running at that cycle. So it's a vicious circle. You have to have some memory that runs at the same speed as your new CPU, and you just do that building it out of the same silicon on the same chip. Right? So it's much, 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 much faster than RAM. It can be 100 times, it can be 300 times faster, it can be a lot more than that. So in order to get things between the very few registers and the much greater, we use commands called load and store. Right? So that requires extra instructions in your program. So when you write, C equals or A equals B plus C, that gets compiled and converted into assembler, there's going to be a bunch of load word and store word commands. You never did loads and stores in C, but they're going to get converted to that. So the compiler has to put everything that the CPU is going to operate on, everything, no exception. If it's an operand, it has to be put in a register. There's no way to skip it and go over the registers and go directly into memory, not with MIPS. Except, it has to work the way we spoke about it, but let's put it that way, right? So I did go to A8, right? But what did I do? I had the value for A in a register. I added 32 to it, 8 times 4, and then I went and got that number. And then where did I put it? In a register. So everything with MIPS goes via registers. Why? Because it makes in writing code for these commands much, much simpler. If you know that if you're going to have a mathematics command, you're always going to be talking about register numbers. You're not going to be talking about things that are not in registers and only in memory. That makes things easier. You got to be smart about the way you use registers. Okay, a couple of last things here to kind of add a little more complexity to this. Sometimes what you want to add is a small integer, an immediate value. So let's say I'm stepping through my array with location 1, location 2, location 3, location 4, array elements. What am I really doing? I'm counting up by 4s, right? So how do I write code to count up by 4? Do I have to go and get 4 from memory and store it in a register and add it to the other thing? That seems doable, but so common, maybe there's another way for it. MIPS 4 supports you being able to specify constants. We call them immediates. So here's a line of code that says, this is an add command, but this is a different flavor of an add. I'm going to give you the source location. It's a register, and it has an integer in it. And then the second operand is actually a constant. I'm going to just give it to you right here. And the CPU knows how to interpret that. It knows how to interpret it, what it's actually going to interpret it as. It's got to be a 32-bit number. So it's going to interpret it as, you guessed it, 0, 0, 0, 0, 0, 0, 0, 0. That's 8, 16, 24, 5, 26, 27, 28, 29, 30, 31, 32. When you put 4 as a constant, it's going to turn it into that. And it's going to add it to whatever the integer is in S3 and then store the result. So I'm counting up by 4. This is an example, hopping up elements in an array. If I put -4, I'd be hopping down elements. Here's a negative right here. You can specify a negative concept, constant. So this is done so commonly, the need to specify constants, that there's actually a place to do it. So let's go back over to our sheet and let's go find that command. Here it is, add immediate. And what it's basically telling you to do is to take one of your sources from RS and the other one from some strange field called signextm, add them together and put the result in RT. You'll notice the instruction format changed from R to I. So if I go down here and I look at I starts off looking like R. The opcode's the same. RS and RT are the same. But instead of whatever these things were, we instead set aside 16 bits for an immediate. 16 bits is a lot. That means you can have, if it's only going to be positive integer, up to 2 to the 16th, 32,768. That's, or 16,384, I think. That's not bad. That's not a tiny number. So you get a lot of constant room to maneuver there. So they made the common case fast. One register is called 0. It's a real register. It's in the chip. It's 32 bits. If you look into it, are always unwaveringly never anything but all zeros. And why do we have it? Because the value 0 is used so commonly in assembly code, maybe not in your code, but we'll see lots of examples of where we use it in assembly code, that we actually gave you an easy way to specify it. We just gave it a register name and set aside a register for it. So it actually is a register. So if you want to add 0 to something, you can just add $0 to something. There are times when you want to do things like swap locations of registers or substitute values, and you can use an add command to do it. It's down on the number of commands you have to have in your instruction set architecture. So here's an example of where took what was in S1 and put it in S2. Well, I could use a move command to do that, but it's faster to use an add command. Just add 0 to S1, put the result into T2. Adding 0 will never change the value of whatever is in S1, and end up in T2 with S1. So this is like move S1 to T2. A little quirky, so we'll find some examples of things like that. Okay, last thing I want to show you here before we bail out is, if I can get over to the book, I want to show you something of the textbook. Patterson, super pokey when I'm running WebEx. All right, here we go. In the back of the book are appendices. And if you go to Appendix A, which, wouldn't you know, isn't linked into this PDF file, so I'm going to have to do it the hard way. And you dig way into it a little bit, you'll get to a section that looks like this, very repetitive, right? Lots of rectangles, things like that. So I'm going to back up a little bit, and it's in A10. And what it shows you is for every command, just like that data sheet did, but sometimes it puts extra little hints and tips in here, and it shows you a little bit more detail. So it's an alternative to the data sheet. The other thing that's beautiful about it is, you remember the add command? We saw that it said 0/20 up here for opcode and function. We didn't talk about function. So know that if you want to tell the computer to add something together, you're going to put the value 0 in the first 6 bits. You'll put your options into the next 3. You'll put a 0 into 5 bits shown here. And in the last 6 bits, what were those 6 bits? Well, down here in this format thing, it was called function. That's where we're going to put hexadecimal 20. Why did we have to do that? Because of this table. And we'll talk more about this several more times in class, so I don't want your eyes to glaze over with it, but see if I can zoom in on it a little bit. I want to zoom in if I can. So what this is showing is, if your 6 bits of your opcode, in other words, the values in bits 26 through 31, are 0 in decimal, or 0 in hex, which turns out to be the same thing, then you are going to follow this top line. You're going to end up over here, and it's going to tell you you need to look at the 5 lowest order bits in the function field. And if you find that the 5 lower order bits in decimal are 32, which is what hex 20 was, come down here to 32. Here it is right here. And what I'm really trying to tell you to do is addition. I'm trying to tell you to add. So a 0 in the opcode field and a decimal 32 in the function field means add. Right? So that's what they're telling you. Scroll the page. There we go. That's what they're telling you here, and telling you over here. So you're going to put a 0 in these 6 bits and 20 here. Why? Because we ran out of combinations of opcodes. There are lots and lots of commands that have a 0 in the opcode function. Add, and, jump register, nor, or, set less than, shift left logical, all of them have a 0 in the opcode. So if you try to figure out what's needed just by looking at the opcode, you don't know enough. You got to look at the function code as well. And then there's lots of other commands where you have a 24 in the opcode. You don't need to tell me anything more. I know you're trying to do load by sign. You tell me 2 in the opcode, I know you mean jump. All right, so that's kind of the basics of where this stuff is going. I We'll always send you an email when there's a new homework to do. I'm putting the finishing touches on the one due for Sunday. Give me feedback on the labs. You know, I want to make sure you guys know what to do and are through them. You should to your TAs on that. So if you're hitting wrinkles with it, let me know. Thank you very much for your time and attention today. Have a great week, and I will talk to you guys soon. I'm going to take a look at chat. Yeah, lecture folder. All right, great. All right, have a good one. Bye, everyone. You will get homework solutions for 1 and 2 to study from, absolutely. We're waiting until Friday to release the solutions for homework 1 because some students were added to the class just in the last 3 or 4 days, had time to catch up. So we're trying to give them a little bit of a break, so just be aware of that. And then homework 2 will probably release at the same time. I'll talk to the TAs. The TAs are making those calls.